Hi grade 12s. We're moving on to the second topic under this unit of applications of calculus. Now we actually are trying to work towards something pretty awesome, but we've got to put some pieces of the puzzles together first, and this is one of the pieces of the puzzle. This is quite a fun topic though. It's called the Newton-Raphson method. Now what my introductory paragraph says there is it says many situations are modeled into an equation. Now that's true in the real world. Most things in life are modeled in the science world, in the business world, in the finance world, are modeled into an equation. And often, in order to solve the problem at hand, you need to solve that equation. However, many solutions to equations are irrational, and many equations aren't these perfect little equations like a quadratic equation, in which case, how do you solve them? So for a quadratic equation, we have a quadratic formula. For a cubic equation or equation of degree 4, there's a formula that works for that too. Your calculator can solve these for you because they have those formulas programmed into them. But what happens if you're trying to find a solution to an equation that has no formula? And the answer is that there's this technique or an algorithm. It's an iterative process. It's basically when you repeat a process of approximating a solution until you get as close as you possibly can. And this method is called the Newton-Raphson method. It's pretty cool. Now, most of these solutions that we're going to go and find are going to be irrational solutions. So we're not actually going to ever be able to find these solutions exactly because they're irrational. However, you can find them accurately to as many decimal places as you'd like. So you could find them accurately to 100 decimal places if you want. Of course, by the time you get to so many decimal places, the difference is completely negligible. And so we generally, solve things to 5 or 6 decimal places, and that's accurate enough for us. So our first example is just going to be looking at how this process works. What does the Newton-Raphson method look like? So I've written a box on the side, and what we're going to do here is follow the steps visually on my graph to see what this means, and then we're going to look at the algebra behind this. So I drew a random graph. This is a cubic graph, so it's not particularly exciting. But let's pretend that I'm trying to find this x-intercept. Right, now what's our first step? Our first step is guess an x value close to the desired x value. Now that's one of the only problems with this method is you can't guess any number, and we'll discuss that later on as to what can go wrong with your guessing process. So you have to kind of graph. You can always use a graphing package in the real world to graph a graph that you're thinking about, and so you can kind of get an estimate of where the root is going to occur, and then you can use this process. So you have to have some idea of what the graph looks like, or you have to know the domain under which you're expecting a solution. So basically we're going to guess an x value close to the desired value. So I'm just going to choose, this x value here. So I'm going to let my first guess be x number 1. So first step, guess an x value. Let the guess be x number 1. So I'm going to plot this point. Step 3 says plot this point. It is point x number 1 and the function value at x number 1. So that's step 3. Step 4 then says draw a tangent to the graph at this x value. Now, it's not very easy for me to draw tangents and use rulers on the screen, but I'm going to try. So bear with me. Let's pretend that, that looks terrible. So let me just try that again because that just looked absolutely shocking. So if I try and draw a tangent, and this one looks equally as shocking, but you know what, we're just going to go with it. One last try, third time's a charm. Let's try again. It's very difficult on the screen. So that looks much better. Okay, so that looks much better. So we draw a tangent to the graph at x number 1. Now step number 5 says determine the x-intercept of this tangent. So for example, that would now be the x-intercept of this tangent. And we call that value now x number 2. Now as you can see, that x is now closer to my desired solution than when I started. So I have now found an x value closer to the desired solution. So it's now more accurate. I mean, it's still grossly inaccurate, but we're going to keep going. So now it says repeat steps 2 to 6. So I'm going to repeat this, and hopefully, and I say hopefully because we'll come to the pitfalls of this method at the end, hopefully I'm going to get closer and closer and closer. So what was step 2? Step 2 was, well, guess your x value, but now we've found an x number 2. So step number 3 is plot this point on the graph. So this point is now x number 2 and the function value at x number 2. Step 4 is draw a tangent to the graph at this point. Again, I'm going to try my best, hopefully better than the last time. So draw a tangent. No, not my best. Draw a tangent to the graph at x number 1. Now at x number 2. And determine the x-intercept of that tangent. And now you'll notice, I'm going to call this x number 3. That's even closer to the x-intercept that I'm looking for. And now I repeat this process. So basically, this entire Newton-Raphson method centers around the idea that you have an x value that's a current approximation. You plot the point on the graph. So my current approximation, plot my point on a graph. Draw a tangent to the graph at that point. And the x-intercept of that tangent becomes your next x approximation. And if I could zoom in here, I mean, if I look at that, that pretty much looks like I found my root. Of course, if I could zoom in and this was an actual graphing package, you would see that you're always going to be slightly inaccurate. But if you keep on going and keep on going and keep on going, you will get closer and closer and closer and accurate to as many decimal places as you want. So this is the idea. Plot the point, draw a tangent, find that x-intercept, and that's a better approximation than the last one. And then you repeat, and you just get a better and a better approximation. So it's pretty cool. Now, what does the algebra behind this look like? So let's have a look. My first point was let the first guess be equal to x1. So that's where we started. Be x1. Plot the point, f x1 and f of x1. Now we needed to find the tangent and the x-intercept of the tangent. So we need to find the x-intercept of the tangent at that point. And that point was x1, f of x1. So I need to find the x-intercept of that tangent. Well, first of all, I need to find the equation of that tangent would be nice. So let's have a look. What tangent am I looking at the moment is this original blue tangent there. So if I'm looking at that tangent, how could I find the equation of that tangent? Well, the gradient of that tangent would be change in y over change in x. This is the x-intercept, so that is the point x2, and, oh, sorry, I'm zooming out now. So let's zoom in again. This is the point x2, and if I was going to add a y value, it would be 0. So my gradient would be 0, because that's the y value at this intercept. Remember, I'm trying to find the gradient of that blue tangent, and I'm going to subtract the other y value, which was f of x1, all over change in x, which is x2 minus x1. So what have I done here? I'm trying to find the x-intercept of that tangent because that will be the next approximation. So I've started by trying to find the gradient of this blue tangent. And so my gradient of my blue tangent lands up being m, which is minus f of x1 over x2 minus x1. Now, what we hopefully know is that the gradient of that tangent is the same as the gradient of the graph at that point. So if this graph was f dashed of x1 is the gradient of the graph at that point. So let me just explain this to myself. This is the gradient of the graph at x1. But we all know from our calculus experience so far that the gradient of the graph at x1 is the same as the gradient of the tangent at x1. So this is equal to m. So instead of actually using m equals, I can now use f dashed of x1. So f dashed of x1 is actually equal to minus f of x1 all over x2 minus x1. Now, what were we trying to find here? What was the whole point of this? The whole point of this is we're trying to find the x-intercept of this tangent. Now, what in this formula actually represent the x-intercept of this tangent is x number 2. X number 2 is there on my graph. That is the x-intercept of the tangent. So this is my x-intercept of my tangent. In which case, I want to rearrange this formula to make x2 the subject. So therefore, I want to rearrange to make x2 the subject. Because the idea is that I need to find this x-intercept because that's the next approximation, and then I can repeat this process. Now this isn't particularly difficult to do really, because I'm just going to multiply by that denominator. So I multiply by x2 minus x1. So I get minus f of x1 by itself now. Then personally I would divide by f dash. So then I would get x2 minus x1 by itself. If I divided by f dashed of x1. So basically all I've done there is divided by that factor. And now in actual fact, these brackets aren't meaning anything now, so I could actually drop them, which means I simply need to add x1 to both sides. So now I get x2 is equal to x1 minus f of x1 all over f dashed x1. So I didn't actually end up finding the formula for the tangent because I actually didn't need to. Simply by looking at the gradient of the tangent, I could solve for x2, which was the x-intercept. So this little formula, I mean, we've never seen something like that before. It's quite bizarre. But that formula works out the x-intercept of this tangent. Now that's wonderful, but x2 wasn't exactly accurate. It was closer, but not accurate. Well, then we repeat the process. Now instead of redoing this whole thing, that means that x number 3 will be x number 2 subtract the function valued x2 divided by the gradient at x2. So you'll notice we can just repeat this process over and over and over again until we get it accurate to as many decimal places as we want. Which means, what is the formula? Now I've run out of space, so I'm going to go here. Now you can either use N or R, I've seen both, but basically on your formula sheet for AP Maths, it'll say if you want to find the next approximation, so the n plus 1th approximation, what does it equal to? It equals to the nth approximation, subtract the function value at that xn divided by the gradient at that xn. So all that is derived from is from taking this process which we figured out and replacing the fact that basically the next guess is just based on the previous guess and that same formula. So I'm hoping that made sense. So in summary, we basically used the gradient formula and our 2 points to work out a formula for gradient and then to isolate x2 because that was the x-intercept. And then we could use exactly the same formula just with x3 and then x4 and x5, and then we could generalize it to xn or xr, whatever variable you wanted to use. Now this is all very wonderful. You never actually have to derive this, but it's very nice to see how it works because it's so nifty and so clever. And also because I truly believe that until you know why something is working, you can never use it properly. I also think you can't understand why it would go wrong sometimes, which is really important. Okay, now equally important as to this wonderful formula is to understand, okay, so what does this actually look like? So let's look at a couple of examples. First example says, given x cubed minus x plus 1 equals 0. So as you can see, that's a cubic equation. I'm pretty sure that we could work this out without Newton-Raphson, but we're using a situation we're familiar with to try and practice. Using x is equal to negative 1 as an initial value, determine an approximation for x correct to 5 decimal places. Well, I always write down my formula, so I figure out what I need. So my formula for my formula sheet says the next guess is the current guess minus f of xn divided by f dashed xn, which basically means I need a formula for f, and I need a formula for f dashed, and I need a calculator. So first of all, what is f of x? Well, f of x is equal to x cubed minus x plus 1. Now, something I've probably failed to mention is that, did we notice that this method finds x-intercepts? So that's why you have to be solving an equation equaling to 0. The Newton-Raphson method finds x-intercepts. So that's why you have to have an equal to 0 in order to be using the Newton-Raphson, because you would have noticed in the picture it's an iteration around finding an x-intercept. So that's why it'll work in this situation. Now, other thing I need is f dashed. So this is a cubic. This should be really easy for us. So f dashed is 3x squared minus 1. And there we go. So basically, the idea is that if x number 1 is equal to negative 1, that means that x number 2, and I'm going to follow the formula, x number 2 is going to be equal to negative 1 minus f of negative 1 all over f dashed negative 1. And this is where your calculator is amazing. What you're going to do in your calculator is you're going to, let me just write myself a note here, this is the calculator. You're going to write negative 1 equals. So you push in negative 1 and then you push in the equal sign. Now why we do that is you definitely do not want to be doing this with every single next guess, especially when the next guess now becomes irrational. You don't want to be putting in values. So you want to teach the calculator how to do something and then just to repeat that process, which is why you need negative 1 as the answer. So you put in negative 1 and you push equals. So now this is stored as the answer. So you will know from other stuff we've done, if we want to use that, you just use answer. So if you want to do negative 1 plus 1, you go answer plus 1. And what's pretty cool is if you push answer plus 1, it'll tell you 0. But then if you just push equals, 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 it keeps on taking your new answer and adding 1. So now what we're going to do is we're going to perform this thing, except we're going to use the answer key. Because then what can happen is that when we want to do it again, we just push equals, 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 and the calculator will redo the same calculation, but using the new answer. So we're going to say on our calculator, we're going to write answer, because negative 1 was the answer, minus, now we need to do f of the answer. So we're going to go answer cubed minus answer plus 1 all over 3 times answer squared minus 1. And then we push equals. And you don't have to show any of that working. All you need to do in an exam is simply write underneath this, okay, what's x number 2 equal to? So I show this formula personally for the first x. And then after that, I just push equals and write down the values. So try it on your own calculator. So answer minus, and then put in your fraction, and put this into your calculator to check if you can get it right. Don't push equals at any point along the way, because you want your calculator to repeat that entire calculation just with the new answer. Now, if I did this correctly, I get minus 3 over 2. Now, even in an exam, we don't show any more working. We simply write x number 3, and all you need to do is push equals, because your calculator will redo the entire thing but with this new answer. So if you push equals, I now get 9 minus 31 over 23. Now I never actually write down that because we want accurate to 5 decimal places, so I can't see what the decimals are if it's in a fraction form. So I write at least the first 5, so minus 3, 4, 7, 8, 2, 6, and that's at least the first 5, and then you push equals again, and you keep on going until the first 5 decimal places are accurate. So if I push equals again, I now get minus 1 comma 3, and you can see that's 3, 2, so it's still changing. So you're getting closer, but you clearly are still quite, well, I say quite far away, I mean you're fairly close when you're talking, second decimal place. So push equals again, and now I get minus 1 comma 3, 2, 4, 718, and you'll notice that we're now at least constant to the first two decimal places. And we keep going. Now, especially if it's going to take a lot, you actually don't have to write down all of them. You can just keep pushing equals until the first 5 decimal places stay the same. So now my next one is 1,324,7,179. So you'll notice I now have 32471, 32471. So you'll notice I have the first 5 decimal places being accurate. Now, I often just push equals a couple of times, and what's interesting is now when I push equals, just out of interest, x number 7, I get minus 1,324717,957, I think. And you'll notice as many times as I push equals, it doesn't change. Now, it's not changing because it's not changing because you've found the intercept. This intercept is irrational. It's not changing because your calculator can only be accurate to a certain number of decimal places. If you're using Excel, which has something like 63 decimal places, the decimal places beyond the end of this will be changing. But your calculator just can't do that. So therefore, what is my solution accurate to 5 decimal places? Well, 32471, that's 5 decimals. And if I'm rounding to the first decimal place, my 7 will round my 1. Now, you don't leave it as 32471 because you know the next decimal place is a 7. And so if you don't round up, you're actually being a little bit inaccurate. So what's the x value in this case? It's a minus 1,32472 if I round to 5 decimal places. It's pretty cool. Again, you don't have to show much. You literally just write down the first couple of x's and then you can write down your answer. Cool, let's try another one. Example number 3 says, show that f of x, now this is a power 5 equation. Now we don't have any ability to solve this on our calculator, so we have to use the Newton-Raphson method. Show that f of x has a stationary point on the interval x is an element from 1 to 2. Now, I have no idea what this equation looks like. I'm assuming it looks a little bit like a cubic going up and down, but I need to show it has a stationary point. Okay, well, what do I know about stationary points? Stationary points are where the gradient equals 0. So f dash x in this case will be 5x to the power 4 minus 3x squared minus 4. Now, remember that Newton-Raphson method only solves equations equal to 0. So it's pretty good that we're solving a stationary point here because we're going to make that equation equal to 0. Now, how do I show if it's at a stationary point between then? Well, a stationary point means that the graph has a gradient of 0. Now, I don't know where it has a gradient of 0, but what I can do now is I can say, right, what is the gradient at 1? And I can sub in 1, and because this is AP Maths, you really don't have to show substitutions. You literally can just write down the answer. So the gradient at 1 is negative 2, which means that this graph is clearly going down at this point. Now, what's the gradient at 2? So what's f dashed of 2? Again, please don't worry about showing any working. You literally can just write down the answer. And if I work this out correctly, which I hope I did, I get 64, which means now, oh, sorry for that, which means this graph is jumping, going up now. So I shouldn't draw it like that, looks terrible, but basically it's going up. Now, this is a smooth graph. It's a polynomial, so this is definitely a continuous graph. So if it was going down and it's now going up, it has to have had a stationary point. Now, that's not always true because there could have been an asymptote or something like that, but this is a polynomial, so this is a smooth function. There couldn't have possibly been an asymptote. So you have to have had a stationary point. So I'm going to say, therefore, my gradient changes. Therefore, f dash x changes on x as an element. I should say changes sign. I shouldn't just say changes. What does that mean? Changes sign from 1 to 2. Therefore, you must have a stationary point. Okay, and here's the fun part. Determine the stationary point. Okay, now this is pretty cool. We are trying to solve f dashed equals 5x to the power of 4 minus 3x squared minus 4. We're trying to solve that is equal to 0. Remember, that's what this equation does. This equation solves an equation equal to 0. And so that's really good. Now, the problem is that the formula is a little bit confusing now because we're working with gradient. The formula says that the n plus 1th derivative, the nth plus 1 estimation is xn minus f of xn all over f dashed xn. And now this is a little bit confusing because this is f dashed, and so you kind of want to put it in there, but careful, no. This function is the function you're trying to solve, and we are trying to solve f dashed. So in this particular case, this denominator is actually going to be f dash dash, and so sometimes it gets a little bit confusing. And so what I often do is, instead of calling it f dashed, I'll call it something different. I'll call it like g, and then I'll change my formula to being g and g dashed. I'm sorry if that doesn't make sense, but otherwise I sometimes get confused where I must use f dashed, because actually I'm trying to solve f dashed equals 0, which actually means f dash dashed is the first derivative of f. So you know what, it's easier to change the name of this function. So now it's easy, because now I know that g dashed is 20x cubed minus 9x, I think, and x1. Well, you can pick anything. I generally pick slap bang in the middle. So I would pick 3 over 2, because 3 over 2 is halfway between 1 and 2. So what is x number 2? Well, x number 2 will be 3 over 2 minus g of 3 over 2 all over g dashed of 3 over 2. So what I would do now is pick up my calculator. Don't forget that you need to use the answer button. So you put 3 over 2 and you click answer. So you click equals, and now it's the answer. So then you go answer minus, and now I use this formula with my answer on top, and I use this formula with my answer on the bottom. Definitely try it for yourself. Now, as I was actually doing that, I was busy checking my work, and I see that I actually have made an error, because I'm not too sure why I thought that was 9. I think I was squaring the 3, but when you bring down the 2, you multiply 3 times 2. So I've just gone and fixed this on my calculation, but that's now a 6, so my apologies. So what do I actually get as my second answer, if I'm correct? I make mistakes all the time. Please do check this yourself, but I get 1,25106836. And the beauty is now I can just keep pushing equals. I just love it. It's so clever. So x number 3, now it's set to 3 decimal places, so it actually doesn't have to be particularly accurate. The next one is 1388, so you'll notice we're bopping around a bit, and then 2222. X number 4, oh gosh, is 1,11595, so we're bopping around quite a bit. But finally, I've gotten 1,115 again, and it's 1150, and if I just check and I put equals again, I still get 1150. So therefore, my stationary point is at a value of 1.115, accurate to 3 decimal places. Now, while we were bopping around, is obviously the intercept, the tangent was going to one side of the intercept, and then the tangent was going to the other side, and it almost spirals around. It's very common to do this. It almost spirals around to the answer. That's pretty cool. Now it says classify the stationary point to question number C. Now that's actually pretty easy. So I'm going to do this here. I've run out of space. And why is that easy? Well, because of all the work I've done in question A, I can pretty much see it's a local minimum, because my gradient was negative before and then it's positive afterwards. So I don't really have to explain, because it said classify this point. If it was for a certain number of marks, it would said explain, I would say because for x is less than 1.115, your gradient was negative, and, running out of space, for x is greater than 1.115. I should probably say greater than, less than equal to 2, because I don't know what happens beyond that. I only checked at 2. So again, I should say greater than equal to 1 here, because I didn't check beyond that. It could change derivative again, but the point was that f dashed, shouldn't be saying f here. I can actually, sorry, f was the original function. F dashed x was positive. If it just said classify without explanation, though, I could just say it's a local minimum. So, pretty cool question. Let's do some more. Example number 4. Now, I like this question because this question says, consider sine of x equals 1 over x. Now, this is a sine graph equaling a hyperbola. I mean, we would have no way to solve this equation. This question says, show that there's a solution between x is equal to 1 and x is equal to 1.5. Now, the most important thing about this is, remember, this Newton-Raphson method only solves equations equal to 0. So this particular, a point of intersection between two graphs is not solvable. It is solvable. It's not solvable in this format. So I first have to say, right, what equation is this? This is sine of x minus 1 over x equals 0. Remember, you're always trying to find an x-intercept. So I need to manipulate what this question is doing, which is actually trying to find a point of intersection, into, can I find where something equals 0? So now let's call this function f of x, because if you were to plot that function, you would be finding the x-intercept. So show that there's a solution. Well, I would say to myself, what is f of 1? Now, don't forget you'd be working in radians because this is in paper 1. So just check on your calculator and go shift mode and put it in radians. Very important. So if I go sine of 1, and then if you don't work in radians, you would get a really bizarre answer, and then minus 1 over 1. And I get an answer of negative 0.1585. And what is the function value at 1.5? And again, just make sure you're in radians. Sine of 1.5 minus 1 divided by 1.5, and you get, and guess what? You get a positive. Now again, why is this important? Well, because that means that whatever this graph is doing, the function value is negative before. So if I draw an x-axis idea, that means that the graph is below the x-axis at 1, and then above the x-axis at 1.5, because this is positive. So the idea is, if this is 1, you've got a negative value, and if this is 1.5, you have a positive value. And so this graph must have gone through the x-axis. Why do I know that? Well, this graph does have an asymptote because I know x can't be 0, but x not being equal to 0 would be down here. And so there's no reason to assume that there would be any issues, and it would be a continuous graph for this portion. So if it was negative before and positive afterwards, it must have gone through 0. So I would say, therefore, must have gone through f of x equals 0. So determines x value to 4 decimal places. Excellent. Remember, you have to have the equation in the form something equals 0, and we do. So what do we need to know? We need to know what f of x is. And f of x is sine of x minus 1 of x. We then need the derivative, which trig differentiation. The derivative, well, I should probably maybe write in brackets that this is sine of x minus x to the minus 1, because I need it in that format in order to differentiate. So sine differentiates to cos, and x to the minus 1 will actually simply differentiate to plus x to the minus 2. So all we've got to do now is do our first guess and then use our calculator. So x number 1, I always guess halfway, so let me guess 1.25. So now x number 2 would be equal to 1.25 minus, and it'll be f of 1.25 divided by f dashed 1.25. So, running out of space again, let's try to use our calculator. So don't forget when you use your calculator to use your answer key. So I get x3 is equal to 1.094047, and you just keep going. Keep pushing equals until you notice that the first 4 decimal places are constant. So I get 1,1137836. I hope I haven't made mistakes. It's so easy to make a mistake. So in an exam, these are worth a lot of marks because it takes time to do this, and you also should always check. So I haven't kept constant yet, but finally I start keeping 1,114157. Yep, It's pretty constant. So therefore to 4 decimal places, I think that's what the question said. So 1, 2, 3, 4. But notice I'm going to round up here because the 5th decimal place was a 5. So I'll round that up to a 2. Cool. So these graphs intersect. Now, let me just say this again. I can't find the point of intersection thinking of it as a point of intersection. I must kind of configure the equation so that I'm always solving an equation equals to 0. Great. Last one for us to try. Exercise 5. Okay, what does this one say? Determine the x-intercept of y equals e to the power of negative x minus cos x, which lies on the interval 1 to 2. Now it just says determine the x-intercept. That's perfect because you would be making this 0, which is exactly what you want. So I know what y is. Y is e to the negative x minus cos x. So now I need y dashed. Now we know the derivative of e to the x is e to the x. So it's that, except the exponent here is negative x. And so that's the inside function. So I multiply by the derivative of negative x, which is negative 1. Now derivative of minus cos x is minus sine x, which you will notice actually becomes plus sine x. So actually y dashed is negative e to the negative x plus sine x. Again, I would guess the first one at halfway in between. So I would guess the first one at 3 over 2, which means the second derivative is, the second approximation is a better way to say it, is follow my formula. So x number 1 was 3 over 2 divided by the derivative of 3 over 2. So don't forget to use the alpha e for the e to the power of. And if I did this correctly, again, I'm hoping I didn't make errors. It said to 3 decimal places, so I only need a couple. And I just keep on pushing equals. So I now get 1.2927, so I'm still not consistent to first 3 decimal places. Now I get 1.2926. And if I push equals, I get 1.2926. 1.2926 every time. So therefore I am accurate, and I can say my x value is 1, now it said 3 decimals, so 1, 2, 3. So my fourth will round that up. So it's 1.293. Pretty cool. Right, now I know this is a long video, but just to quickly talk through potential issues, because this is quite quick. What could possibly go wrong? Well, there's 2 things that could really go wrong. What happens if, just per chance, what happens if the initial guess that you make actually happens to be a stationary point? Now, the method was you plot the point, so that's x number 1, f of x number 1, and you would then draw a tangent, and then you find the x-intercept of that tangent. This tangent doesn't have an x-intercept because it's parallel to the x-axis. And so there is no second approximation. If you also think of the formula says the next approximation is equal to this. And guess what? The derivative at this current approximation is 0. And so the formula actually breaks down because you get undefined. But visually it breaks down because this tangent does not have an x-intercept. So if I say no x-intercept, therefore visually there's no x number 2. Now, what are the chances that you randomly guess the stationary point? Well, I suppose in a cubic or something easy you could. So that's the first problem. Easily fixable because you just go slightly different. Now, the second problem, which can come up a lot and cause a lot of problems, is what happens if your first guess is close to a stationary point. And so what happens then is your tangent is quite shallow. If I was trying to find this intercept, for example, if I guess there, my tangent is quite steep, and so immediately I get closer to my value. But if I guess quite far away from and this is why we said you must guess close to. If you guess a little bit far away, and so now it's closer to a turning point, the graph's very shallow there. So now what happens is my tangent is very shallow, and so my x-intercept is very far away. Now, that's only a problem because if I go down to where my graph is and I draw my next tangent, you'll notice I'm now going off in another direction. So x number 3 will be there, and guess what root you're actually going to find. You're going to end up getting closer and closer to this root. So you will be finding a root, but you just land up finding an incorrect root. So just because you guess something far away doesn't mean you won't get an answer, and that's the problem. You will get an answer, but it's not the one you were looking for. So that's why you have to guess close enough so that you're not near another stationary point making the graph shallow and the tangent goes off quite far away. Now you should be able to pick this up if it happens, because if x number 2 is down here and you're suddenly getting an x value way bigger, then you must worry a little. So that's the second type of problem that you can get, which is why it's quite important to know a little bit about what the graph looks like before you start guessing. Great, and that is the Newton-Raphson method. I hope it makes a lot of sense. It's something which it's a method that I really love because I think it's beautiful. But I'm hoping that it made a bit of sense to you. Cool, well done.